Sometimes buildings seem to defy gravity.
In this program, we're going to look at the ancient Leaning Tower of Pisa, the incredible Puerta de Europa towers in Madrid, and a modern classic, the Torre de Collserola in Barcelona.
Buildings and structures rely on their foundations to keep them upright, and their foundations rely on the ground beneath. The challenge is to find a solution which uses the ground effectively and doesn't overload it.
To explore this subject, we're at the site of one of the most famous structures in the world, in the beautiful Italian city of Pisa. The Leaning Tower is the campanile or belfry of a large complex of religious buildings, including the great cathedral, the baptistry, and an ossuary dating from the medieval period when Pisa was at the height of its power. Built to a height of 179 feet, the tower is essentially a hollow cylinder containing a spiral staircase that ascends to the bell. Both the inner and outer surfaces are faced with white marble.
Construction on this remarkable building was begun in 1173 by Bonanno Pisano. At that time, the sea was a lot closer to the town than it is today, and Pisa was a rich and successful naval republic. The bell tower was to be one of the tallest campaniles in the land, to call the Pisans to worship.
Records suggest the building began to lean as soon as the first floor was completed. What is known for certain is that building work stopped in 1178 after reaching the fourth floor and was not started again for 100 years. The Pisans had to go to war with Genoa.
The reason for the tilt lies in the soil beneath the tower. The soil here is a soft clay, highly compressible and sensitive to changes in groundwater level. In this case, that means changes in the sea and the river, and crucially, from the effects of the construction of the then new cathedral just over there. It was a bit like trying to build a tower of bricks on a soft mattress.
By the time the construction had reached the fourth floor, its weight was 9,500 tons, and one side had gone down half a meter relative to the other.
It's such a strange feeling on the staircase, because here on the south side, it's as though the stair is leaning away from you, and suddenly you climb around the corner, and the stair is absolutely precipitous. It's nearly vertical. As the soil consolidated over time, more on one side than the other, it became stiffer, and the direction of lean changed from the north to the south. But nevertheless, they kept going. Construction was restarted in 1272 by Giovanni di Simone.
After 6 more years of building, the tower weighed 13,800 tons, and the settlement on the south side had reached nearly 1 meter. The bell chamber was finally built between 1360 and 1370, but to make the bells hang straight, the bell chamber obviously had to be vertical.
Here on the overhanging south side, there are 1, 2, 3, 4, 5, 6 steps up to the bell chamber. But here on the opposite side, there are just 1, 2, 3, 4 steps up to the same chamber. This is what gives the upper part of the tower its characteristic curved shape. It's an extraordinary structure, a real achievement for its day. Today we understand more about the properties of the soil below and the stability of the tower, but to the Pisans of the 13th and 14th centuries, their moving tower was nothing short of a miracle. It was a sign that God was on their side in the wars with Genoa, a sacred icon, a place of pilgrimage. As we come around the side of the tower here, we can see where the stone's been pulled apart by the tower leaning over. Masonry is an incredibly robust medium, and this is just a perfect demonstration of that. Here there are cracks opening up and then closing, and here the stone's been actually chipped off in the corner where it's been forced together. Lovely. Over the centuries, as the tower continued to lean and sink, it pushed up a mound of earth on this side, which helped to slow up the movement. Amazingly, to reveal the stonework, this was excavated in the 1830s, after which the rate of lean increased dramatically.
In 1990, it was recognized as a danger and was closed to the public. At present, the tower leans some 15 feet from the perpendicular, putting huge stresses on the south side. The tilt is increasing all the time, and in the early 1990s, the tower was also found to be rotating.
Works are now in progress to stabilize the tower for good. The Italian government was finally spurred into action following the collapse of a civic tower in Pavia. The first step was to secure the tower temporarily.
Tons of lead weights were attached to the north side in an attempt to stop the tower from leaning further. But a more permanent solution was required.
The only sensible solution to stop it falling over is to change the angle of the tower. Early schemes proposed props, but it would be very risky to work under the leaning side. The solution that's been adopted is neat and simple and doesn't even involve touching the tower. Small volumes of soil are extracted by drilling down under the tower from various points around the north side, leaving tiny cylindrical cavities. These then squeeze shut due to the pressure under the tower. By choosing in which areas to excavate, the tower can be steered back from the brink.
If successful, and trial results are so far looking positive, the repairs will extend the life of the tower by 200 or 300 years and should stop the rotation completely.
The aim is to reduce the angle of tilt by ½ a degree. That's just about ½ a meter at the top. Of course, they don't want to straighten the tower completely, because at the end of the day, it's the lean that brings the visitors.
The medieval masons must have been in awe of their moving tower, not understanding the subtle movements in the soil beneath. Pisa lost the war with Genoa, but its tower has assured its place in the world.
But what if you really wanted to design a leaning building? Well, that's exactly what's just been done recently in Madrid.
The incredible twin towers of the Torres Puerta de Europa straddle the main road north out of the city. Translating as Gateway to Europe, the towers are both office blocks, one occupied by one of Spain's major banks. For me as an engineer, these structures are simply unique.
Wow, they're absolutely fantastic. Look at these huge, great black towers leaning right over the road to Madrid. Each one leans 3 times as much as Pisa, and they're twice the height. Not a lightweight piece of architecture, this. It's a really powerful statement.
But these buildings aren't just Latin exuberance. There's a good reason for their extraordinary design.
At the planning stage, restrictions on the site meant that the towers had to be 140 meters apart at the base, potentially diluting their impact if they'd been ordinary vertical buildings. The architect decided to link them visually by leaning them together. It's a bit of a stunt, but it works. They really dominate the whole space. Incline buildings are very unusual and they require special engineering design. But the principles are simple. The most critical question is the most obvious. How do you stop them toppling over?
The overhanging upper stories want to tip the building forward, so the simplest solution is to weigh it down at the back in the foundations.
Down below me, under each basement, is 14,000 tons of concrete, acting exactly like the lead weights in Pisa to counterbalance the lean of the building. That's enough concrete to cover this entire area 10 meters deep. So the counterweight stops it toppling, but what stops it bending and sagging? Every building has to be stiff enough to hold its own shape, but in these inclined towers, the problem becomes even more acute. The steel and concrete frame of the building has to form a rigid skeleton holding it upright. So the shape of the frame is very important.
The great silver triangular shapes that you can see so clearly on the side of the building give it a lot of stiffness. Triangle shapes are useful in building frames.
And I can easily show you why by sketching it. Use a napkin. Imagine a three-sided shape and a four-sided shape, and we try to squash them by applying forces at the corners. The three-sided shape stays rigid because none of the bars can move anywhere. But the four-sided shape is easily flattened. So the triangle is a much stronger shape in structural terms.
The problem of the building sagging is most serious during the construction of the frame, before the building has its full stiffness. So to correct this, there's another system to keep it stiff.
Imagine my arm was the building. If I stretch this rubber band, it pulls my fingers back and straightens and stiffens my arm. Down the back of the building here, there's a system of steel cables running from the top to the bottom, anchored to the foundation, which does exactly the same job.
During construction, by tightening up the cables, they use them to straighten the top of the building by 150 millimeters. And if they need to, they could still tweak it further today. It's called post-tensioning. If you look at the space between the top and the bottom of the building, there's only a few meters in which they overlap. It's in this space, between the top and the bottom, that a huge concrete backbone supports the construction.
Wow, and here it is. The concrete core is huge at the bottom of the building, and it also houses the lifts. Let's take a trip up. Here at ground level, you can see the street outside. The lifts are at the front of the building. We'll see what happens when we get to the top. Right, here we are. At the back of the building. There. Well, this is the top of the highest building in Madrid, and there's a heliport here. Isn't it fantastic? What a view!
When they were completed in 1990, the Torres Puerta de Europa instantly became a landmark in Madrid. It's a distinctive gateway which dominates the local skyline.
Office buildings so often put costs before creativity. Most are very bland and boring, but it's really refreshing to see something so original. For the engineers, this must have been a very exciting project.
As we've seen, keeping a tower standing upright is all about controlling the forces going down. But across Spain, in Barcelona, we're off to find a fantastic expression of this. Barcelona has an impressive array of wonderful architecture, combining traditional Catalan buildings with flamboyant new design. Commissioned in the run-up to the Olympics in 1992, the Torre de Collserola is a state-of-the-art telecommunications tower.
Wow, fantastic. Coming up out of the city into the Collserola Park, green trees and a blue sky. You can really appreciate the stunning beauty of that white tower. 288 meters tall, it's almost as high as the Eiffel Tower, on top of a mountain.
There are 13 floors, all but one designed for satellite dishes and transmission equipment. In fact, the tower is big enough to house 700 people and relies heavily on brilliant engineering to keep it upright.
Traditionally, communication towers have mostly used open steel lattice structures, like the grey electricity pylon behind me. But if the new tower had been built in this style, it would have required an enormous base, and it would have looked like a giant industrial pylon, totally incompatible with Barcelona's stylish image. The city saw the new tower as a chance for something much more unusual.
A British architect, Norman Foster, won the commission. His design reduced the structure to its bare elements. The tower is a simple, hollow, circular concrete shaft. 13 floors are wrapped around it and held in place by a system of steel trusses and cable stays. Above the concrete shaft, an 80-metre telescopic steel tower, like a car aerial, reaches skywards. Right at the top sits a small crane for lifting equipment up and down.
Under the bottom of the tower, down there, the main foundation is a simple concrete disc, 20 meters in diameter and just 5 meters thick. It didn't need to be thicker because the tower is founded on rock, not soil. But such a tall, thin shaft would be much too flexible without another system to stiffen it. So the tower uses steel cables, like guy ropes, to hold it down, counteracting the effects of one of the major threats to towers, the wind. Up here, wind gusts can reach very high levels. The wind is known as the tramontana, and it blows from the northwest, rushing over the hills. Gusts can reach well in excess of 100 miles an hour. That's pretty serious. 3 sets of high-strength steel cables anchor the tower down to huge concrete blocks like this, each one 800 cubic meters, 2,000 tons of concrete.
The cables are tensioned so that even in a high wind, they will never go slack, and that ensures the tower remains stiff.
In a 60-mile-an-hour wind, the top floor will move only 85 millimeters. That's just this much.
The huge forces in the steel cables pull down on the tower and up on the concrete foundations simultaneously. But any long tube under compression bends easily, so it needs to be braced.
The tower is a hollow shaft like this piece of tubing, but if I compress this between my hands, it bends and collapses easily. So how did the designers get around this when it came to the tower? Here we are on one of the floors of the tower that's still being fitted out. It's a curved triangle in shape, held up at each of the corners by a giant steel frame. The frame's pressed onto the tower by the cables which run down below and up to the top. Remember the tube? The frame acts like a brace around the tower, just like this, making it much stiffer.
Notice how lots of shapes in the structure are triangular. As in the towers of Madrid, this is where the tower gets much of its strength and stiffness.
There's a lot of equipment on the tower. This floor is for television. Each of these is a different local station. This one's for picking up outside broadcast units. Hope we don't get in the way.
You may be wondering how they built a 13-story block way up here. Well, the answer is they didn't. The floors were actually built on the ground and lifted up here by jacks. It took 4 days to lift the structure into place.
Finally reaching the top floor, inside the concrete shaft. Stretches way above us. But we can't get out that way.
These cables from the top of the frame to the top of the tower cross in front of the microwave dishes. They're made of Kevlar, an immensely strong man-made fiber, as strong as steel. But unlike steel, Kevlar cables are invisible to radio waves. We're 155 meters above the bottom. This great tower is quietly buzzing away. But all around us, these cables, the steel frame, and the concrete shaft are all carrying huge forces, locking this extraordinary structure into its exact position. It's a masterpiece of engineering. There's no doubt that the tower met with the city's brief to construct a monumental technological element. The tower is unquestionably a dramatic symbol of Barcelona's commitment to innovation.
Engineering is the art of the possible. To make the Leaning Tower safe for the future, to break with convention in Madrid, or to combine beauty with function here in Barcelona, all have taken extraordinary ingenuity. And that's what it's all about.
In our next program, we sail to the Eddystone Lighthouse in Plymouth, investigate the gigantic floodgates protecting Rotterdam from the sea, and fly out to the largest structure ever moved on Earth, the Troll gas platform.